physics project, I chose to explain the physics of a yo-yo. And I mean, a yo-yo seems like a pretty simple toy, but there's actually some really complex physics behind it. A yo-yo itself is comprised of 3 cylinders, 2 of which are equal mass and radius on the outside to balance it out, and 1 of which runs through the middle, which is of a different mass and radius. But the cylinders themselves are equally distributed as to keep the yo-yo balanced at all times. So there's a lot of mathematical concepts that actually work behind a yo-yo. So I am going to describe them today. So I thought I'd start with the hardest one, which is the moment of inertia. The moment of inertia, for those of you who don't know, is the rotational analog for mass. So where mass is to acceleration and force, this moment of inertia is to angular acceleration and torque. So that's the analog. So the reason that it's not as simple as you would think to find the moment of inertia is because there are 3 parts. So what I'm going to do is write a general equation, and then I'll be able to use it for all 3 cylinders. And you'll see here the mass of the 2 cylinders on the outside are different from the one on the inside. The width, L is going to be the width today, of the 2 cylinders is different from the one on the inside, and the radius of the ones on the outside are different from the ones on the inside. So using these general variables, we can come up with one equation for cylinders and apply it. And that's how you find the moment of inertia of a yo-yo. So next, I'm going to focus on the energy that's involved in a yo-yo, and I'm only going to focus on the mechanical energy. I know that in real life there's some friction, there's some sound that are expelled from the yo-yo, and that's a loss of energy, but that's really, really complex. So to help you understand, I'm just going to stick with the theoretical method, which is perfect world. Frictionless, soundless, spinning perfectly, energy conserved. So in the case where energy is conserved, potential energy initial is equal to kinetic energy final. And I'm defining the height, in this case, to be the length of the string. So we're going to pretend that when the yo-yo is released, it's just going to go to the floor. And since it's frictionless, it won't be hurt, or it won't be stopped anyway. So, first of all, potential energy. So now is where it gets kind of tricky, because in order to do anything further, we have to do torque. So first of all, I'm going to set a frame of reference here. When considering a yo-yo that's moving, we have to be really specific about what we're considering and when we're considering it. So in this case, when it's speeding up in the angularly, rotationally, the only thing that's acting on it is the string, and the string is acting specifically on the inner cylinder. Well, when we consider the moment of inertia, we have to consider the whole thing. So in some of my calculations, the ones where I'm dealing just with tension, I'm going to be specifically referencing the inner cylinder. But then when I'm trying to generalize it, I'm going to have to go back to dealing with the whole thing. So what we have to do is use torque. I'm going to move over here. Using our combination of equations, rotational, translational, kinematics, force equations, we were able to cross off most of the things on our list. We were able to get the moment of inertia, we were able to get kinetic and potential energy, we were able to get acceleration, we were able to find velocity, we were able to find, we used the bridges, so if you use the bridges you can find the angular acceleration and velocity, which is not that hard. You just take the acceleration and velocity you found and divide them by r. So the only things left on the list to explain the motion of a yo-yo are momentum, both angular and translational, which really aren't that hard because angular momentum is equal to I times omega, and linear momentum is equal to mass times velocity. So we've already found the I previously using that big long equation m1 r1 squared plus m3r3 squared all over 2. So we found the I earlier. We found the velocity, and we have the acceleration to plug in there. So that would get kind of complex if you plugged it in, but you can do it to get the actual value and use the bridge to find the value for this. And again, for this, you just plug in the A. So really, we found all of the mathematical components, but there are a couple of other things that describe the motion of a yo-yo. There's friction and there's sound specifically. And I said earlier for the calculations we're not going to discuss them, but they are kind of important because of the fact that yo-yos are based on friction. When they are on their way down, they don't want friction. You don't want friction. You want them to spin as much as possible and as freely as possible. But once it gets down, it'll spin freely. So you want it to have some friction, or else you can't get it back up. So friction is actually a really important part of the yo-yo, and is sound as well, because they're both energy escaping. So you only want to have the two when you absolutely want to. So that brings me to the next part of this, improving a yo-yo. This particular yo-yo, if you can see here, uses a sort of clutch that flips on and off. So you can either have it on auto return, where it'll get to a certain speed of spinning, it'll come right back up, or you can have it on regular mode, which is what a yo-yo is supposed to be, where if you turn it off, it will go down, keep spinning until you want it to come back up, and then if you can get it to catch, it'll come back up. So what I thought was the best way to improve yo-yo maybe just to improve on that clutch. Rather than having the yo-yo slip to sleep at the bottom when the clutch is on, so like here it'll come back up, but if I throw it down hard enough, then it'll sleep. I'll show you that right now. When you throw it down hard enough, it does this, or once it slows down enough, it'll come back up. So rather than have a simple clutch that has it slip and then slow down enough where the friction will catch, my idea is to have the string actually like attached to the center cylinder, so that instead of slipping, it will be the entire cylinder rotating. So the cylinder itself will not be like a true cylinder, it'll be locked into the left and right cylinders, the outer ones. And at the bottom, there'll be a sensor inside of this, which will detect when the tension is greater than the weight of the yo-yo. Because when it gets to the bottom of its path, the tension is momentarily greater, because all through here the tension is less than or equal to the weight. At the bottom, when it's spinning, when it's sleeping, it'll be exactly the weight. But at that moment when it's changing from moving to at rest, it will have a tension greater than the weight. So there'll be sensors in this that can detect when the tension is greater. And what it will do, it'll have this clutch system, but it'll be different. It'll unlock whenever the tension is greater than the weight. So it'll make it more efficient, because rather than having a mechanical system, you can have a computer that can detect it, and you can use materials that are more frictionless. So you can have a better, longer sleep and have it easier to transfer your hand, because when you pull back up, the momentary increase of tension will cause the clutch to turn back on again and pull it up. So it'll be easier to use, it'll be better for tricks, I think, and it'll have less friction, improving the efficiency of the yo-yo all around.